So I think we need to take the case, so we can find many empty seats here. So uh, maybe in the next class we will take the pub case. Okay. Okay. So please check your attendance on the Blackboard. Okay. Okay. So okay, let's review what we learned in the previous class. So we learned about the various type of flip-flops, deep flip-flops, right? So I mentioned that we frequently use flip-flops in our digital design. So and then I also explained why. So this is the reason why we require deep flip-flops in our digital design, because we need to also control the timing of our digital systems, right? So using deep flip-flops, so we can also control when the output signals are reflected, right? So if we use deep flip-flops, so signals, if this is the kind of deep flip-flop, so the signals are just updated the right after the rising edge of clock, right? So actually on the rising edge of the clock, but we can also observe some delays. So that's why I said right after the rising edge of clock. But theoretically, the signals are updated on the rising edge of clock, but actually we can observe some delays, right? So you can understand. So actually this is the basic model of the digital design, right? So actually we have learned about the combinational logic, but when we build the real digital systems, actually the combinational logic is located between deep flip-flops. So this deep flip-flop just control the timing of input signals to this combinational logic. So which means that the input signals are updated on the rising edge of this clock, right? So actually, because of this deep flip-flop, all input signals to this combinational logic are changed on the rising edge of clock at this time, right? So all signals are given to the combinational logic at the same time, right? And this combinational logic also exhibit delays, right? So after some delay, the output will be changed based on the input signals, right? But actually these outputs are different. So which means that the timing, the delays of this combination logic can vary. vary, vary, okay? So actually we cannot estimate the exact timing of this combination logic. That's what I said, because actually the delay of a circuit is influenced by many factors, right? But the output is also sampled by this deep flip-flop. Okay, so you can find that the output signals of combination logic is also connected to the input of deep flip-flop. So it is sampled. It is the output of combinational logic are sampled only on the rising edge of clock. Okay, so by doing this, we can also control the timing, right? Timing of our digital system. Okay, so which means that we can build stable logic. Okay, so try to understand the this model. Okay, so actually we will also learn about some timing of sequential logic later based on this logic. But this is very important. Okay, and then so we learned about the FSM, so finite state machine, right? So finite state machine means that so based on the states, then we can just generate some output signals, right? We define a certain state using FSM, and then based on some various states of FSM, we can generate output signals. So like this system, the output, so output of a certain system can be determined by current system, right? So this is the example of a system, right? So so using the circuit, we can also make some system. So and then this system includes states, right? And then based on the states, the output signals are determined. Okay, so that's why we require to build FSM for our digital systems, right? So FSM is composed of state register and the combinational logic that determines next state and output signals, right? And then we also learned about the two types of FSM. So it's a Moore FSM and Milli FSM. So only difference between the Moore FSM and the Milli FSM is the output signal is determined by only the current state, that is the Moore FSM, right? So that can be the question of the pub quiz for the next class, right? And then in the Milli FSM, the output is determined by current state and input signals, right? So this is the Milli FSM. So only difference. So the only difference between Moore FSM and Milli FSM is that output can be in the Moore FSM, output is determined by only current state, right? So you can find that the output logic in the Moore FSM output logic receives current state as input signals, right? But in the Milli FSM, then output logic receives current state and input signal, right? So this is the only difference. Okay. Okay. So now, we will learn how to design FSM. Okay. So this is the design process of FSM. Okay. So firstly, we need to identify inputs and outputs. So you know, in a system, when we learned about the kind of digital system component of digital system, this digital system includes the input signals and output signals. When we design a certain system, we firstly need to define input signals, right? So actually, I mentioned that this system is kind of a black box. And then black box received a certain input signal, and then we can define the output of black box, right? So firstly, we need to identify input and output signals, and then okay. So this is the system. Firstly, we need to define inputs and outputs, and we need to define functional specification, right? So functional specification is that based on the input, then outputs are generated, right? So this is the functional specification. So this is the FSM design. So which means that we need to also define states, okay? And then, so if we design FSM, then states will be changed by input signals, right? So this is the example. So it's the same. The states, there are multiple states in FSM, and then these states are changed by input signals. So, so we can define the state transition diagram. So the state transition diagram looks like this, okay? So we can define states, solid, liquid, and gas. And then based on the input, the states are changed, right? From current state to next state. So if we can just connect the state transition based on the input signals. So this is the state transition diagram, okay? So we can sketch the state transition diagram, right? So then we define how states are changing, right? And then we can also define the output. So based on the state transition diagram, then we can also define the output based on the state, current state. So we can make the FSM, FSM. So for the FSM, the outputs are also influenced by input signal. FSM, the outputs are just determined by current state, right? And then FSM, the outputs are defined by input signals. So based on the state transition diagram, we can make some table. Okay. So think like this. When we build combinational logic, firstly we define truth table, right? And then in the truth table is the all possible inputs, and then also truth table exhibit the output signals based on some corresponding input values, right? So we can make the state trend. So in the FSM, we also need to build combinational logic that determines output states at next states and output signals, right? So like this. So next, you can find the next state logic and then output logic. So next state logic determines the next state, and then output logic determines output signals. So we need to build combinational logic in FSM. So like the truth table, we can make the table also. And then so I mentioned that we need to make two combinational logic. That is the next state logic and output logic. So we can make the state transition diagram, a state transition table based on the state transition diagram, and then we can make the output table. Okay. So FSM, so we need to make the separate table because the output is also just determined by current state. But in the FSM, we can combine this transition table and output table. So I will show later. And then select the state encoding. And then we can make the Boolean equation. And then finally, we can make the schematic logic. Okay. So actually, so I'll show the example. So okay, you don't need to memorize this. Okay. So Boole FSM example. So that's what I showed in the previous class, right? So in this example, so let us assume that So we are requested to design traffic signals. Okay, so this is the intersection, right, for the horizontal horizontal road and then vertical road, right? So we need to define the traffic signals. Okay, and as I mentioned, in United States, actually the United States does normally the traffic signal does not include the left turn signal. Okay, so we can define the traffic light for this horizontal road, and then traffic light for the vertical road, right? So we can define the output. Outputs are the right of this traffic light. And then what is the input? So let us assume that these traffic lights are controlled by some traffic, the vertical traffic, and then vertical traffic, and then horizontal traffic. And then let us assume that the road has the sensors, the traffic sensors. So if the traffic is detected for this horizontal, then the horizontal traffic is detected by TA, it's a traffic sensor, and then the vertical traffic is detected by TB. So we can define input signals. The input signals for this system are traffic sensor signals. Okay. If the traffic is defective, then TA is 1. Then if the traffic is not detected, then TA is 0 for the horizontal traffic, right? Then based on these input, we need to make the output signals. So output signals are the values of traffic light. Okay? Okay, let's start. So firstly, we can define input signals and output signals. So you can find the black box here. It's a traffic light controller. Okay, so this is the system we need to design. Okay, and then we can define input and output signals. So as I mentioned, we need to use the inputs from traffic sensors, right? Those are TA and TB. Also, this is the sequential logic, and then sequential logic that includes D flip-flops. So we require clock signal and reset signal. So in order to make the state, in order to make a stable system, I mentioned that we require a reset signal, right? So these are inputs, and then what are outputs? LA and LB. So the traffic light values are output signals. So we can define inputs and output. And then based on the inputs, and we can also define the output values. Okay. And then, so this is the example of Moore FSM. So which means that outputs are just determined by current state. Okay. Then how many output combinations are defined? How many output combinations are need to be defined? So this is the system, okay? And then we need to define output values, right? LA and LB, right? And then there are 3 different values like green, yellow, red, right? It's a traffic light, right? So LA can have green, yellow, red, and then LB can also has green, yellow, red, right? But these are traffic lights. So green is not allowed, right? Because so if it's unstable signal, if LA and LB generate green and green, right? So we can define output combinations, right? So if the LA is green, so okay, so it's a LA and the LB. If LA is green, the horizontal line is green, road is green, then LB needs to be red, right? And then a certain traffic, the vertical traffic is detected, then we need to change the traffic light, right? So if the detected, then it goes to the yellow, but it is still red. The LB is still red, right? It's a yellow. Then it goes to the red, right? And then it is a green. And then if a traffic is detected for the horizontal road, then it is goes to yellow, and then this is still red. So we can define 4 possible combinations, output combinations, right? So this is Moore FSM, and then I mentioned that we can define four possible output combinations, which means we need to define 4 states, right? Right. So there are 4 different output combinations, and then in the Moore FSM, the outputs are just determined by current states, right? So there are 4 different outputs. So which means we need to define 4 states in Moore FSM, right? Do you understand? So you can find the 4 different states from S0 to S3, and then each state includes the output signals, output values of traffic light, right? So the green, red, yellow, red, green, and then red, yellow. So based on the output signals in Moore FSM, we can define states that is corresponding to the output signals. Okay, so we define the output, the state of the Moore FSM. Then in FSM, the states are changed but based on the input signals. So we also need to define state transition. So state transition means that if a state is changed from a certain state to the next state, then it is called the state transition, right? So, and then based on input signals, the states are changing from current state to next state. Okay, so in this system, we have 2 inputs, the clock and reset signals are required for flip-flops. So actually, this FSM includes the 2 input signals, 2 control inputs, right? Those are TA and TB. So we can define the state transitions based on the TA and TB. So in this system, so S0 is the LA is green and then LB is red. So which means that this is the horizontal. So LA is green and then LB is red. And then if the traffic is still detected for this horizontal road, then we need to keep the traffic light. Okay. So if the TA is the sensor, right? The traffic sensor. So if the TA is 1, then TA is 1. Okay, so state is, if the current state is S0, then the next state is also S0, right? So it is because we need to keep the output if the S0 if the traffic is still detected, but traffic is not detected, so not TA. So you can find the bar here. Then it goes to yellow and red. Okay. And then if the current state is yellow and red, then it needs to go to S2, red and green. So so this is not possible, right? So this is traffic signal, right? So if the current traffic light is yellow, then it goes to red, and then this is green. Okay, and then also this state transition is determined by the TB, right? So and then if the TB is 0, right? So which means that traffic is not detected, then it goes to yellow, and then still red, and then it goes to the S0. So actually you can find that for any cases, for any inputs. Okay, so these are state diagrams. So this is a state diagram for this system, right? So firstly, we define inputs and outputs, right? And then based on the input and outputs, so this is more FSM, then we can list the output combinations, and then based on the output combinations, we can define state. So because in Boa FSM, the number of states is equal to the number of possible output combinations, right? Then based on the input, the states are changed, right? Then based on the input, we can define state transitions, right? So if you see the this state transition diagram, then you can find the arc, okay, like arrow, and then you can find the input values here, right? So when we define a state transition, we use the arc and input values. Okay, so this is the state transition diagram. And then based on this state transition diagram, then we can make a state transition table and output table of this Moore FSM. So we define system, and then the next step is design. So we need to design logic. Okay. This is the state transition table, right? So we can find the small state transition diagram here. Okay, so I will explain based on this. So how can we make the state transition table? So in a state transition table, we need to define output the next stage, right? And then more actually all in all FSM, all types of FSM, next states are determined by input signals and current state, right? So we need to list the current states here, right? And we need to list the inputs for this current state. So let's see this S0. If the current state is S0, then there can be two possible input cases, right? So you can find the two arcs from this S0, right? So this arc and this arc, right? Based on the input TA and TA bar. So for the current state S0, we can define two possible inputs, right? And then based on the current states and input values, we can define next stage. So if you see this state transition diagram, we can easily know the next state by current state and inputs, right? So if the current state is S0 and input signal TA is 1, what is the output? What is the next state? The next state is S0, right? Because you can find this arc. It starts from S0 and then it also returns to S0, right? So if the S0 and then TA is 1, then what is the next state? Is S0, right? And then if the TA is 0, then it represents this arc. So this is S1, right? And then if the current state is S1, then actually for all input combinations, so don't care, then the next state is S2, right? Then if the current state is S2, we can define two input combinations, okay? So S2 and TB is 0, then this is the next state is S3, right? So you can find this arc here. And then TB is 1, this is still S2, S3, and then the next state is S0. So it's not difficult. So if we define the state transition diagram, then based on this state transition diagram, we can define state transition table. So in the state transition table, so the left side is the current state and input. Then the result is the next state, like this. So this is the answer. Okay. So, but in the state transition table, so we can find some text characters, right? But we need to design digital systems. So which means these states. So we define the current states as 0 to from S0 to S3, like S0, S1, S2, S3. But these are not kind of digital signals, right? Which means, so actually we need to represent these states name as digital signals, right? Digital values, like 0 and 1. Okay, we need to use zeros and ones. So actually, this current state, so like the S0 and S3, needs to be represented using digital values 0 and 1. So this is called the state encoding. Okay, so we don't need to use the text characters, like the letters, like the S0 and S3. Good. So this state's name need to be encoded using digital values. Okay. Next state is the same. We cannot use the letters. Okay. So this state name needs to be encoded using digital values. So we can encode the state's name using digital values like this. So S0 is 0, 0, and then S1 is 0, 1, and so on, right? So this is the encoded digital values. Then using this encoding table, we can change the state's name using the encoded digital values. Like this is S0, okay, S0. So, but this is 0, 0. And then output the next state. The next state the same. So this is S1, but we need to use the 0, 1. So because based on this encoding table. Okay. So if you see this table, then you can find that this table is similar to truth table, right? So this is the left side of the truth table, like the 0, 0, 0. Don't care, then output is 0, 1, right? And then 0, 0, 1, don't care, then output is 0, 0. Okay? Okay? So we complete the state transition table, and then you can observe that so the states are encoded using digital values. So if you see that this state transition table, then it is similar to truth table. And then if we define a truth table of a certain logic, then we can build combinational logic, right? So that's what we learned in this course, right? The truth table is defined, then we can make Boolean equation, and then we can make truth combinational logic. It's the same. In the FSM, we define state transition table using digital values. Then we can make the next state logic, because next state logic is a combinational logic. Okay. The output table is the same. Output table is actually very simple. Okay. Because in more FSM, the output signals are just determined by current state, right? So this is the current state, S0, S1, S2, S3, and then these are defined output values like green, red, yellow, red, red, green, red, yellow. But we cannot build combination logic using these outputs, like so, because so which means that the output values also need to be encoded using digital values. So we can encode these output signals like the green is 0, 0, yellow is 0, 1, and red is 1, 0. Okay. So, and then we need to use the encoded value for the states. Okay. So this is S0, S1, S2, S3, and then these are encoded values, right? So this is green, then this is right. This is red. Okay, so you can just encode it. Okay, green is 0, 0, yellow is 0, 1, red is 1, 0. So based on this encoding table, we can define the output value. So what's this? This is truth table. Okay, so this is the input, right? So current state is the left side of the truth table, and then based on this input, then we can generate the 4 output bits. So from LA1, LA0, LB1, LB0. Okay. So what does that mean? We can define truth table for these output values based on the current state. And then once we define truth table, and then we can build combinational logic. Right. So we define state transition table using digital values. So we can build combination logic for next state logic. And then we define output table, okay, using the current state. And then based on this table, we can make combinational logic for the output signals. All right. So we can make the combination logic, so Boolean equation. Okay, then let's see how to make a real circuit. So let's see the FSM schematic. So state register determines state of this FSM. Then this is the register. Why? The register represent multiple D flip-flops, right? And then we require 2 bits for representing state, right? So in order to represent 4 different states, we require 2 bits, okay? Here. So this is the D flip-flop. So actually this is the D flip-flops, okay? And then so there are 4 different states from S0 to S3, and then in order to represent these 4 different states, we require 2 bits from S0 and S1. So what is this value? This value is current state. Okay. And then you can find the input of this state register, that's input of D flip-flops. What is this input? This is the next state. Okay, so you can find the S-0 and then S-1 here. Okay, so these are next state bits. Okay, so these are next state. Okay, so what can you observe? So you can find the reset and clock signal. So next state is reflected to current state when on the rising edge of clock. Okay, so this is the state register. Okay, so state register is actually D flip-flop. Then the input of this state register is next state. Then the output of state register is current state. So which means on the rising edge of clock, the current state becomes the next state. The next state is reflected to current state. Okay, understand? So then what is required? So if you see the where's the war machine? So this is the war machine. Okay. So you can find the state register here. Okay, as I mentioned. Then the next state logic generate the next state, right? So in the Bohr FSM, And then actually all in all FSM, all types of FSM, next state determined by it's generated by input signals and current state, right? So this is the next state logic. Next state logic is the current state and input. Okay, so that's what we already generated, because so we already generated this table, so state transition table. So the current state and the input, and we can define next state. So based on this state transition table, then we can generate, we can figure out Boolean equation. Okay, so this is the Boolean equation for S-1 and S-0. Okay, S-1 and S-0. And then using this Boolean equation, we can build the combinational logic. Right? So this is the Boolean equation. So then, which means that we can define combinational logic for this next state logic. So you can observe that the next state logic receive the S0. So we can find the feedback S0 here, and then S1, so current state, S1 is also connected, and then also the TA and TB are used for generating S-1, S-0. Okay, so this is the next state logic, and then we can build next state logic based on the state transition table. And what is required next? And then we can define output logic. So output logic, this is the Moore FSM. So output logic is just determined by current state, right? So S1 and S0 is just used, and then using the output table, we define the truth table for the output signals based on the S1 and S0. So we can also generate the Boolean equation for these output signals. So based on the S1, S0. So we can find that only S1 and S0 are used for generating LA1, LA0, LB1, LB0. So this is the FSM design. So firstly, we define input and output, and then we define state transition diagram. And then based on the state transition diagram, we can build the state transition table and output table based on the state transition diagram. So if we use, then the states and output values need to be encoded using digital values, and then all signals are digital signals. So we can build the combination logic for the next state logic and output logic. Okay? And that's it. This is the completed FSM design. Okay. So FSM includes the sequential logic. Actually, it's very simple. Flip-flop. Okay. And then combination logic. That's what we learned. Okay. So actually, it's a mixed. So this is the sequential logic design. So, and then if you see this schematic, then also you can find that this schematic is equivalent to the conceptual schematic of Moore FSM, right? here. So it's a more FSM. So this is the next state logic, and this is the output logic. Then this is the state register. So this is the state register, and this is the next state logic. This is the output logic. Okay, so which means if you see this schematic, then we can figure out, oh, this is more FSM, right? How? You can just see the output logic. The output logic is just determined by what? Current states. So, the inputs are just connected to the next state logic. So this is more FSM. And okay, so we build the circuit. Then let's see the diagram, the timing diagram of this FSM. Okay, so you can see the waveform here. So this is the clock signal, and then this is the reset. Okay, so this is not a negative reset. Okay, and then this is a synchronous reset. Okay, so this reset is asynchronous. Okay, so which means, so if you see the state transition diagram here, then you can also find the reset signal. So when the reset signal is 1, then what is the state? What is the output state? The next state is S0. But this is the asynchronous reset. We assume the reset is asynchronous reset. So which means if the reset is 1, then the output is immediately reflected. The output is changed immediately by reset signal. So when we define state transition diagram, so we need to also define the reset state, the initialized state. So if the reset is 1, then the state is S0. Okay. So this is, so I mentioned that we require reset state for generating stable system. So reset is 1, reset becomes 1. Then we can find that the S0. So this is the current state, right? And then this is the S dash. So this is the next state, and then this is the current state. Okay. And then these are output, right? Because this is the LA and LB. So if when the reset becomes 1, then after some delay, then it becomes the S0, right? The current state becomes the S0. What is this one? So output, the next state is the combinational logic of current state and input, right? So before reset, you can find the 2 question mark, so which means, oh, we don't know. So before the reset, actually we don't know the current state value. So it's kind of X. So it's the unknown. Okay. So because the current state is unknown, the next state is also unknown. But when the reset becomes 1, then the current state becomes S0, right? Based on the definition, S0. And then the next state is the combination logic of current state and input. So we can find the input signal here. So based on the current state, then we can also define the next state, because this is the combination logic. Also, if you see the output values like LA and LB, so you can find that this is unknown because the current state is unknown, but the current state is determine, and we can also observe that output values are determined. Okay, and then the reset is 1 and reset becomes 0. Okay, so in the state transition diagram, so this you while the reset is 1, then it is determined by this arc. Okay, but now the reset becomes 0, right? It becomes 0 here. Then we need to consider this part. Okay, so we just ignore reset. So after this time, this clock cycle, then we need to consider this transition diagram. So this is the normal state. So now the current state is as 0 here, and the reset is 0. So no, it's a normal state at this point, right? So, and then we can check the input signal. Okay, so input signal TA is 1 and TB is 0. Okay, then so TA is 1, so actually it's 0. The next state is at 0. And then TA becomes 0 at this point, right? Then what is changing? The input is changed, right? So and the input is asynchronous, right? Asynchronous means that okay, so it's not synchronous with the clock signal, right? The input is changed at this point. So what is it changed? Next state, because next state is the combinatorial logic of what? Input and current state. So input is changed. So we need to define, so we can know the output values are also changed. So next state is changing immediately when the input signal is changing, right? So S1, it becomes the S1. So this is just the next state, right? So if you see the state register, then this is clock, and then clock, and then this is next state, and then this is the current state. But you can find that current state is not changed. Why? Current state is the output of D flip-flop. So current states are synchronized with the clock signal. So you need to know, you need to understand. So next state is the combinational logic of input and current state. So input is changed. The next state is immediately changed, but current state is not changed because current state is the output of D flip-flop. It's synchronized with the clock signal. Okay. So you need to understand. Okay. Sometimes you can be confused because because we are not familiar with this the timing diagram of the system, but we need to understand. Okay, so the next state is changed immediately by input, but the current state is not updated. Current state is updated when the rising edge of clock. Okay, so you can find that S1 is here, okay, because this is the clock. So this is the next state, this is the current state. Okay. So on the rising edge of clock, the clock cycle 5, then S1, the current state, the next state is reflected to the current state. Okay? And then based on the current state, the output is determined, the output becomes the yellow. So you can find that next state is S2. This next state is S2 is determined by this current state. Okay, because of this transition. Okay, so as I mentioned, the next state is reflected immediately, but current state is reflected by next state on the rising edge of clock. So you need to understand that this timing difference between next state and current state. So because at this edge, the clock cycle 6, then next state is S2, so current state becomes the S2 on the rising edge of the clock. Okay? Then based on the current state, the arcs are changing. Okay, so you can understand the remaining changes like this. Okay, so here. So try to understand. So this is sometimes so it may be confused because as I mentioned, we are not familiar with some timing diagram. Actually, so we are very familiar with some programming, right? So in the programming, the output values are immediately changed by input values, right? But in real hardware, like this sequential logic, the output, some values are updated on the rising edge of clock, right? Like the in current state. Okay, so we need to understand. So just try to understand this timing diagram. Okay. So actually for this example, we use the binary encoding at the 0 in order to represent the states. We use the binary encoding because so there are 4 states. So we use just the 2-bit signals like 0, 0, 0, 1, 1, 0, 1, 1. So 2 bits are just enough to represent 4 different states, right? But sometimes we can use the one-hot encoding. So this encoding is called the binary encoding. Okay, but we can also use the one-hot encoding. So one-hot encoding means that one state to bit per state. So what does that mean? So using binary encoding, 0, 0 represents the S0, this is S1, this is S2, this is S3, right? So we require only 2 bits, but in the one-hot encoding, each bit, so this is a bit, each bit represents the state. So which means this bit, the first bit represents the S0. So in order to represent S0, we can represent S0 like 0, 0, 0, 1. Okay, so number of bits of this one-hot encoding is equivalent to the number of states. And then each bit represents the state. So with the one-hot encoding, this is S0, this is S1, this is S2, this is S3. Okay, so you can find that only one bit is 1. Okay, because each bit represents states. So if we use the one-hot encoding, sometimes we can use the one-hot encoding because then we can make the simpler combinational logic. But if we use the one-hot encoding, then we require more flip-flops. Okay, more flip-flops. Okay. Okay. So this is the one-hot encoding. So actually, one-hot encoding is very simple. So then we can just use the different encoding rules for the states. Okay, like the 001, 0010, 0100, 1000. Then we can replace the states using the binary values. Okay, and we can complete the state transition table. Okay, so then, okay, let's see some really FSM example. So until this point, I explain how to design more FSM. Okay, now so actually we can once we define state transition diagram, then we can build the state transition table and the up table, and which means that we can build the FSM logic, okay, FSM circuit. So, and then the next example is the milli FSM. Okay. So if you read the textbook, then you can find the same example. Okay. So it's a smiling snail. So there is a snail that crawls down a paper tape with ones and zero. So it's a sequence of 1 and 0. And then if the 01 is detected, then the snail smiles. So it means like the 0001, 0011, 0001 like this. So this is the example of input sequence. Okay, so input sequence of bit data, and then if the 01 is detected, like this one, and this one, then snail, this snail smiles. Okay, so which means actually, so for this input sequence, like this input stream, then we can define we can detect 01. Then how can we build FSM using for this system? So this is the input sequence, okay, 00, so it's a bit input sequence, and then if the 01, this sequence is detected, so 01 is detected, then output is 1. For other cases, output is 0, right? So this is the system. So we can define input and output. The input is the bit data, right? So bit data of this input sequence. Then what is the output? The output is the behavior of snail. So snail is, if a snail smiles, its output is 1, then otherwise output is 0. So firstly, we can define input and output. Then based on the input and output, we can define FSM, the state transition diagram. So firstly, if we just assume milli FSM, so we need actually in the milli FSM, the output. So in the milli, you can find the arc here, arc in the state transition diagram, and then actually you can find the slash here. So in a milli FSM, you can find the different signal is actually on the arc. So this represents the input. This represents the output. Okay. So what is it? So when we learned about the Moore FSM, you can observe that the Moore FSM as like S0. Actually, the output is defined inside of state, right? Because the output is determined by only current state. Then what is different? In the milli FSM, you can find that, oh, this is state, but we cannot find any output here. It is because in the milli FSM, output values are determined by input and current state. So in a milli FSM, output is here. So this is the output of milli FSM. So in the Mo FSM, output is here. Okay, inside of state, the Mo FSM. But in the milli FSM, output is here. Okay, so in order to detect the 0, 1, take the sequence. So this is the input sequence. So firstly, we need to detect the 0, right? So if the 0 is detected, then we can know. So if the next input is 1, then output needs to be 1. Then if the next input is still 0, then output is 0. But it goes to this state. So firstly, 0 is detected because we need to detect the 0, 1, this sequence. So if the 0 is detected, then the output is determined by this input, right? So we just define the two states. We can define the two states. So this state means that S1 means if the next input is 1, then we can detect the output. S0 represent, this S0 means that it's the opposite state. So that means actually even if the next value is 1, but still the output is 0. Okay? So in a milli FSM, so it's S0, then if input is 0, then it goes to the S1 state. So if S1 state means so it's kind of next is 1, then output can be 1. Okay, so first 0 is detected. Okay, so if the state is S1, then if the input is still 0, then output is 0, and it also goes to the S1 because 0, 0, 1, like 0, 0, 1. So if the first 0 is here, then it goes to S1 because if the next is 1, then we need to detect the 1. But if the next is still 0, then it remains in the same state because it's the same state, right? If the next is 1, then the output can be 1. Okay, so in the S1 state, then if the input is 0, output is still 0. So in the milli FSM, output is determined on the arc, right? But it goes to S1 again, like 0, 0, 1 this case. But if the next input is 1, then it's a 1 and it goes output becomes 1, right? Because 0, 1 is detected. And then the state goes to S0 because if the 1 is the input, then if the next input is 1, then it is still 0. Then if the next input is 0, still is 0, right? So regardless of input values, the output is already 0. This means the S0 state. Okay, so 1, then if the input is 1, then output is 1, and then it goes to S0. Okay, so 1, then it remains in the S0, and then 0, then it goes to the S1. So this is the milli FSM for this name. 이게 좀 느리네요. Okay, so we can define milli FSM like this. Okay, so try to understand that this state trend. So just remember that the milli FSM, the output is represented on the arc, not inside of the state. Okay, so I will also learn about this next class. 네, 감사합니다.